Hey, welcome back everybody. So here we are again, another session of this live coding the Raspberry Pi Pico emulator. And this week is going to be super interesting because the format is a bit different. Unlike all of the other times, the previous sessions where we had some goals, but we didn't know if we were going to hit them. This time I did some offline work, which I'm going to tell you about, so I'm pretty positive that we have already hit the goals that we are going to hit in this session. But let me tell you about it more in a minute. Let's see who is here. So I can see Nekadi and Steve and Jim from Canada and Punith and Tomash. Hello everybody. Let me just know in the chat that you can see me and hear me as usual while I share my screen. And this is our short to-do list. So that's where we left off last time. Yeah, there is like a lot of small things that I would like us to do today. But let's start with something that just landed in my inbox an hour ago or so. So that would be this pull request. Oh, thanks. Energy is okay too. That's good to know. So Turo, which is actually, you might know him as Valerio. He has been in the last few streams active in the chat. So he sent us a pull request and he found that the LR register has the least significant bit set to 0, while in a real Pico at the same position it was always set to 1. So this sounds like a bug that would eventually hit us at some point, and it refers us to manual pages. Let's go there to this page. Probably, yeah. So yeah, I can already see it. Like you see, we are setting the high bit of the link register to the low bit of the link register to 1, and I guess the other one is for BLX. And I guess we forgot to do that when we coded BL and BLX. I think we coded them in the, like, at least BL was in the very first session or something like that. So the pull request is pretty simple. It just bitwise ORs with 1 in order to set that bit. So I will merge it, and he says that the test must be modified to correct the expected value. So let's first of all merge this. So yeah, let's change the commit message to fit our convention. That's called conventional commits. All right. So we have this commit message. Okay, and let's also fix this small typo. And here we go. And I'm really happy that Valerio sent us this fix, because this is the kind of bugs that you could literally spend, hi Anai, good to see you here as well. You could literally spend like hours hunting for them, and in a moment I will tell you how I hunted the bugs from last week, and you will see how similar this bug is to that bug from last week. So you could spend hours hunting for them, and then in the end it's just like a small note or like something like that in the datasheet that you haven't noted. So thanks for noticing. You really saved us a lot of precious time in the future, so I believe. Okay, let's pull the change, and let's just quickly see if there are any failing tests. Let's start a test runner, Wallaby, and we'll probably have some failing tests now after we merge this, just because of the commit message, that message, I suspect. Yeah, we have a few failing tests for those BL and BLX instructions. And yeah, now the LSB should be set. So just, add 1 to fix all those tests. Oh, this one wasn't related. So 5 and 5, and voila. Let's bit2040 fix tests following blx fix c commit. Let's see the previous commit number. So see that commit for details. All right, so one more bug fix to go. It's amazing how little time we spent on it right now, and in a moment I will tell you how much time I spent on the two other bugs. All right, so let's review the two bugs. Last week we didn't quite get the program to work. We tried to get a Blink compiled with the Arduino core. So that's the Blink for the Raspberry Pi Pico, but written in Arduino language. We tried to get that to work in the emulator, and we got this nasty error from maybe we still have it in one of those tabs. Like we have all those tabs that we wanted to yeah, we can actually close all of those. They remind me bedtimes. Okay, so yeah, we had a crash in Mbed OS, and we tried to figure out where it came from. And I started debugging, and one of the first things I did, and somebody left a comment on YouTube that suggested that, so then thank you for that. I just printed the stack pointer value for every instruction that we execute, and I figured out that it went wrong at some point, and it was always on the MSR after an MSR instruction. And MSR, if you don't remember, let's go to the code. That was MSR. What it does, it writes to a spatial register. And then I noticed that whenever you write to this register number 16, the primask, then the stack pointer goes totally wrong. And the issue was very simple. We just missed this break here. And as you can see, this means that every time that you write to primask, then the case will fall through, and will also update the stack pointer, which is a very, very disastrous bug. So if you check the commit message, I actually said it's a stupid bug, and it's a stupid bug because this could be easily avoided, and like I could have saved all the frustration last time, and all the I spent another half an hour just chasing down this bug. If we had a tool that would warn us against things like that. So there is a tool that does that, and it's called ESLint. So I'm adding to the to-do list, to our to-do list, set up ESLint on the project, because we don't want to waste time on that kind of bug. So like missing break or something that an automated tool could automatically catch. And we could have also written tests for this method, but you see that it's not really covered. But I'm not sure, like in this specific case, writing the tests, if they were exhaustive, that would have caught the bug. But then using ESLint would have done it much easier. So I always say use the right tool for the right purpose, and we in an ideal world we would write tests for every single line, but I mean that would also slow us down. So we need to keep the balance. Anyways, so that was the first bug, and if we check the commit history, where is that? Yeah, the commit history, you can see that this was the first bug I fixed after this stream last time. I also added a missing parameter to load hacks, but that was something we already did last session. I just forgot to commit it. We stashed all those changes at the end of the session, and we didn't commit that, so immediately after the session I added that. Then I fixed that stupid bug. And now let's move on to the more interesting bug, the second one. And I think we'll have a look at it in a moment, but I think this is the longest commit message I've ever written for like a 5-character bug fix. So this is the commit message, which explains the bug, and we'll go over it in a moment. And this is the bug fix, just 5 characters, and bitwise not 1, just clear that bit, number 1, like the least significant bit. And at this point, I would like to ask you in the chat whether we just want to read the issue and understand it, or actually see how I found this issue by, removing the fix and then walking through the steps that I did for finding the issue. So let me know in the chat if you want me to walk through it, how I found it. And while I hear your answers, while I'm waiting for them, let me explain to you the bug. So basically, we had this comment that says, this is the original line, and it says, write this to the stack, the value of this.pc. But we had this comment, and if you check out the datasheet, you can see that in the datasheet, let's just copy it. Yeah, in the datasheet, this is push tag, so this is the pseudocode that we implemented here, and you can see that it says that we are not pushing PC. So you can see like we are pushing LR, and here we push LR. So this is pretty much one-to-one, but here we are pushing return address. And I guess when we implemented that, we assumed that return address is this.pc. Which is true for the most part. If we check out the implementation, then we can see that for most exceptions, this returns next instruction address, and next instruction address is just not defined, but I think it's just this.pc. Like they call this function, they don't define it. Amazing. And then there is this instruction address in case of synchronous hard fault exception, but this is not defined as well, and we don't handle hard fault anyway at the moment. So in any case, it returns this.pc. So what we wrote there was almost correct, because we missed, I don't think we even looked at this implementation. But here is a small note saying that this bit, the lowest bit, is always 0. Well, thank you for including the most important bit in this pseudocode in a comment instead of the actual pseudocode. Very useful. Yes, you can guess I'm not really happy with the way this datasheet is written. Anyways, so yeah, so this is the implementation of that node. But why is this important? So the reason it is important is, and I see Punesh says he would love to quickly hear about the chase. So this is like the chasing part, how I found it. So there is this SVC instruction we implemented last time, supervisor call, which raises an exception, and the datasheet says that it accepts an 8-bit immediate operand, and this operand may be interpreted in software. So the emulator doesn't have to do anything about that. It just ignores that, and it's the responsibility of the operating system to do that. And in fact, Mbed OS does that. So there is this SVC handler which reads the value of this IMM8, and how does it know? Where does it read it from? So it reads it from the PC value that was saved to the stack in exception handler. So basically that was right. Yeah, so that was here. It reads it from this memory address, and in order to find that memory address, it loads the stack pointer, the process stack pointer, which is the active stack at that point. Then it goes to offset 24, and 24, I think it's I'm not sure actually how this translates to this, but somehow it works, and it loads this value into R1. And then, oh yeah, this is like 18 hexa now that I'm thinking of it. So yeah, that let's double check that, but I'm pretty sure I did the math right. Yep. So yeah, it loads this address so PSP plus 18 or 24 decimal into R1. Then it subtracts 2 from R1, and that's the key. And then it loads a byte from the resulting address and does something with that byte. But the thing is, when we load this, we are loading the address of PC, and that address in the simulator points to the, or before the fix, if the LSB was set to 1, it pointed to the second byte of the instruction, not the first one. So when we subtracted 2 from it, and that's the next instruction, so we subtract 2 from it to go 1 instruction back, but instead of being at the beginning of the instruction where this actual value, this IMM8 is, we are at a second byte of the instruction, which is always constant, 223. So if we look at SVC, where is that SVC? If we look at SVC, we can see that there is like the high byte, which is the second byte. This is Little Indian, has this value, which is exactly that value that this would always read. All right. Oh, I'm missing 1 at the beginning. So 223. That's the byte that it would read instead of the low byte, which was the first one, which is the IMM8. In case of this, in case of the Mbed OS, that was supposed to be 0, because the next thing we do, we compare that to 0, and then we do stuff based on that value. So that was the bug, and let's see how I traced it down. So last time we were looking at where is that? At SVC RTX message queue get that I don't really remember. We found the sources online, but it tries to retrieve a message from a message queue, and at some point it got some magical value number 4. And then I added some debug prints to see how this 4 got into there. And I found that it's stored in some global variable. So let's try to quickly restore this bug. So where was that? Yeah, that was the bug fix. Let's remove the bug fix. We still need to write tests for that. All right, so now if we load this blink, emulator run, where is this blink? Blink blink.hino.exe npm start. I think it would crash immediately. Yeah, that's... Oh, a funny thing, by the way, it really confused me. You see that there was, like, in the log, there was all those exception errors that we got last time, but then it seems to blink a pin. And it turns out that Mbed OS has a piece of code that blinks the onboard LED in case of an error. So initially when I run it, I thought it was working, but then I checked the source code for the blink program, which I just recompiled in case we modified something, or just to be sure I'm running the right thing. I noticed I'm blinking a totally different pin in my program, so it wasn't my program that was running. And to verify that, I actually, let's do that again now, I set a breakpoint in the setup call, in the setup routine. That's the debugger breakpoint setup. So breaking at the beginning of the Arduino code, and I noticed it would never get there. So I figured out, you see, it's like inside, now if we check the stack trace, it's inside Embeddor, embed HAL system die. That's the thing that blinks the LED to tell us there was an error. So not really useful. Anyway, actually, let's just, I figured out that this 4 was coming from this global variable, OS RDX message queue. There is like this, I love GDB that it prints all this data. There is like this global variable in Mbed OS that has all this data about the state of the operating system. And you can see it has a lot of stuff, including like this timer thread, and you can see it has this message queue set to 4, which is not a valid memory address, so it doesn't make sense. And then I wanted to know how this 4 got into there. So again, I traced who writes to that memory address by adding a console log whenever something writes there. And I found that they call another function called OS message queue new, and this function, and at this point, if we had like the source code correctly set up with the compiled binary, like the debugging environment set correctly, that would have probably taken me 1/3 of the time to debug that. But anyway, that setting it up would also take a lot of time, so it's another trade-off that we have to do. Anyway, so this function, you can see here, it does a bunch of things, and let's set up a breakpoint here. Let's restart the whole thing and set up a breakpoint so you can see this in action. Target remote bin host 333, yes, again, and then let's rake just before this SVC call, and let's let's run, continue, great, and this assembly, and we can see we are in this SVC call, and if I print R0, we can see it's 4 because I don't know why it's 4. Someone not sure where it got a value 4 from. Probably the caller sent us the value from 4. Yeah, it got loaded from some memory address and got 4. Doesn't really matter. The thing is, you would expect that after running this instruction, so inside the service call, it would do something and then return. So as a supervisor call, that would call the operating system. But if I single step, then I can see that okay, this us now. Now it should have raised the exception. So next time we execute an instruction, we should be inside the supervisor call handler. Yes. And now in the supervisor call handler, you will note it does this process. Let's switch to assembly layout I described to you. So I'm going to print out some values as we go. So first of all, at this point, R0 and all the registers should have been pushed into the stack by the service entry code. And if we go, we can see here the piece of code that I mentioned in the commit message where we load the stack pointer. Then we extract the value of PC, the instruction that the instruction after the one that caused the exception, the instruction next to the SVC instruction, and that's it, R1. So this is, you can verify it if you want, but this is like the code that called us, where SVCs is stored. I mean, the instruction after SVC, but here you note this bit is 1, not 0, and that's the point. That's the problem. And now we are removing 1, so PX R1, and you can see it removed 1, but this is still like the wrong value. And then we are loading this value. So if I just do this like that, if I print this value here, you will see, oh, maybe I should have printed it not as an octal. Focus command, print /d decimal. Yeah, let's do it unsigned short int, unsigned car. Yeah, that's maybe this way. Yeah, that should have been that value that we printed before. I'm not sure how to print it now. I'll print. There is like a way to tell it to print it unsigned. Maybe L. Not sure. Anyway, we know that this is like this is like that value 2 to 3. Anyway, so this is the wrong value. It's now going to load the wrong value. So if I print R1 now, we can see, or actually 222. I wonder why it was 222. I think it was supposed to be 223. What did we reason about it there? It's, yeah, not sure why it's loading the wrong value as well. Anyway, this is not 0. It's loading from the wrong location, then it's getting the wrong value. And then you can see that the next thing, so here we are at Svc Handler plus 18. It branches to the end of the function, and then it does stuff and returns. And eventually the method that calls us, yeah, you can see here, R0 is 4, so it returns 4. So basically the issue was that this function wanted to call the operating system handler for creating a new message queue, but because of that bug, this handler wasn't executed and it took the wrong branch, etc. And now if we, so that's basically how I traced the bug. I compared it to the actual Pi and found that in the actual Pi, it read 0 there. Let's see that. Now I restore the bug fix and target remote winhost 333. Yes, whatever, focus on command. Yes, and continue, and it should hit that breakpoint again, again in OS message queue new, and now R0 is still 4, but this time if we go step through the instruction, it will execute the supervisor call, and this time you can see that R1, the LSB is 0, that's the fix, and then we remove 2, so it's still like the LSB is clear. We load a value, and then we can see that it loaded 1. Actually, that's interesting. This one, it might have something to do with the bug we just, I mean, why is there 1 there? There should have been a 0. Interesting. It was 0 last time I checked. Let's try to see. And now, yeah, now it still fails. Interesting. Well, that's interesting. Have we changed anything here? Why did we remove that? Let's just revert and try again. Oh, I killed GDB. Anyway, let's try to run this. Okay, so not sure what happened. We had like some other change that probably destroyed this, but now I think it's okay. Let's see that the kit is synchronized. Yeah, we had, let's do that breakpoint one more time. Do we have the address that we broke in? The one that where the SVC is? Yes, this is the address. Okay, layout assembly, continue. Wait until it gets there. Oh, it doesn't get there because we are already in this good. Now we are in a good place. All right. And Punith, thanks for the calculation on the chat. Anyway, we need to focus CMD, continue, and now it will break. And now we'll see this working, hopefully. Okay, inside the SVC handler, and then R1. Oh, now R1 with the. It will work, yeah, with the lowest bits clear, and then single instruction, loading that. I wonder, there is something about the debugger that I can see it's actually writing there one. Yeah, I guess that there is an issue with the debugger. writing 1 and then it's writing 0. So yeah, so probably debugging this, it's setting a breakpoint or something at that specific point for some reason, the debugger, and that's why we are getting strange values that we don't expect to find there. But anyway, when I debugged it on a real actual Raspberry Pi, the value was 0. Not sure, it shouldn't, yeah, it shouldn't have been 1. Yeah, one of the problems with debugging code that runs differently in the debugger. So if we run the code, we can see that now it's getting into the error state, but if we run it without the debugger, or just don't do the breakpoint, let's just do it without a breakpoint. Yeah, now it works okay. So here we found another sort of another way this bug hits us if we break at a very specific location in the debugger. Anyway, so now yeah, you know what? Let's fix that. Let me show you how to fix that. So, because I'm not happy to be in the situation where I'm telling you I don't know what's going on. We know what's going on and we can fix that. So yeah, we just want to comment that out so it will wait for GDB. All right. Now, instead of breaking at this point where the SVC instruction is, we are going to break one instruction before. So the debugger won't override this instruction with the breakpoint, and we won't get all that garbage when we are debugging. So let's set a breakpoint here this time. No, break at this point, one instruction before. And now we'll continue, and we can see now we did a breakpoint here, and now I finally expect this to make sense. So again, R1, that makes sense. That's the address of SVC where we have previously set the breakpoint. I mean the instruction after the SVC. Now it should point to SVC. You know what? Let's just verify that. This as actually we can just, yeah, no, that didn't work. This as here, that should be the SVC. Yeah, you can see here it's like this address, it's the SVC right after our breakpoint. This time we haven't set this breakpoint here, so it should not interfere with our code. Now we'll step one instruction, and now yeah, you can see that R1 is indeed 0. It read the correct byte from the SVC instruction, and it won't take this branch. It will continue executing this function, and eventually, let's finish this. I'm not sure that finish is going to work though. Let's do something like that. Let's put another breakpoint here in this, just after the SPC. Breakpoint here, so we'll just run until after the SVC call. And now if we print R0, that's that 4 that confused us before. So we can see now we have a valid pointer, and if we print this RTX info, it's still not initialized, but if we just execute a few more instructions, you can see it's been initialized to that value that we have just got from the service call. So basically this is how I trace the bug, comparing the behavior here and that branch that was not taken, that was taken on the simulator but not on the actual Raspberry Pi Pico, because of reading the wrong byte from the flash, trying to find out the argument for the SVC instruction. So anyways, that was it for these two bugs, and I spent I think in total around 6 hours chasing those bugs. I also tried to integrate those into Walkway, which we'll talk about in a moment. So I was like doing other things as well, but the total time was about 6 hours. I don't know how much was the net time for working on this bug. Anyway, if we continue, we can see that now it actually sets GPIO pin 1 too low and then too high, which sounds pretty promising because we set GPIO, like our Blink program, if you remember, works on pin 1. So it seems like it got into setup. And to verify that, there is like some RDOS stuff going on here. But if we just restart the whole thing, we can see that if we just break at setup now and we continue, it actually stops at setup, and we can like skip that line, skip that line, skip that line. Yep. And let's take a break at loop as well. And now you can see that after I go to this digital write in the loop function, if I hit next, yeah, it still didn't write to the LED. Interesting. It says low. Yeah, something strange goes on here. I mean, yeah, eventually it agreed to go, and yeah. Oh, yeah, it said that GPIO pin too high. Not sure why the debugger is like going back and forth between delay and digital write. It's probably something that has to do with the compiler optimization or such. Would know if we looked at the assembly code. But anyway, you can see that at this point, we got this to work. Like it gets into setup and blink, so all the initialization code works. It gets stuck at delay, and I also looked into that. We'll investigate that in a moment. But before that, let's just add to the to-do list. I want to add a test case for the PC LSB bit clearing issue. That was, so we won't forget to do it. And yeah, this is our amazing tech debt section that is going to grow a lot today. No, that was this one. Yep. So if anyone feels like contributing a pull request with that test case, it shouldn't be too complex, or maybe even change the existing test case to fail with the original code but pass with the new one, then you are welcome. Otherwise, we'll do it when we'll get to this section. Anyway, so at this point, I want to show you a few more things I discovered. So first of all, let's just go and edit this code. So code blink. I wanted to see if I can get serial output from this code. Like that would have been amazing if I could print debug stuff, and if I could add debug prints and get them to work. But obviously serial.begin and serial.println, I mean, that's not so obvious. I just tested it with the real Pi Pico, and that works over USB. But Arduino core. What I discovered is that you also have serial1 that is going right into the UART. So if we rebuild this code, let's rebuild it. And now with this serial1, and now let's copy this. Yep. All right. And now we run the simulation again. Let's uncomment this execute, so it will just run it straight away. Is it already running? It is. Yeah. Let's restart this. So at this point, I was super happy to see that we actually get the UART prints. So not only this code runs, we can also get debug prints from the code that is running inside the emulator, and I think that's amazing. And then I was starting to get curious about why delay doesn't work. And it turns out that the reason delay doesn't work here is And that's based on my experience with other emulators. Usually, if it just, if we open GDB and we look where it's stuck, we'll see it's stuck in some kind of idle task. See, it's like idle loop. And then if we continue, it's still in the idle loop. And there is nothing interesting in the stack trace because it has like tasks that it's switching between. So we are not really seeing the stack trace for the loop function and that stuff. I could have tried to debug it, but I imagine that the way to exit from the idle hook would be to execute some kind of it would probably wait for some kind of interrupt. And my immediate suspects were one of those timers. So we have this timer we started to implement, and it has alarms. And those alarms, they can fire interrupts. So that was my immediate suspect. But instead of, going ahead and trying to see if I could implement it, I tried something else. I tried looking which interrupts the code is listening for. So we have this vector register which points to the vector table. So let's print the value of it. So it's this plus that was Vitor. I probably remember it. Right. So this is the vector table. And then if we print 64 first entries from the vector table, so we already know this is like the stack pointer, and then this is like the reset pointer, and then all of them are set to this value, like most of them. Like we have this, this is like where the code begins, the reset handler, but then this one repeats all the time. So if we look at this, it just ISIRQ9. I guess it's like just a fallback for unimplemented interrupt handler. And there are only a few interrupt handlers that are implemented. Specifically, I think the first 16 entries are not used for interrupt. So if we go 16 entries down, no, I don't want to disassemble, I just want to go 16 entries down, we can see there are like a few handlers for the first interrupt and then for this interrupt. What is that one? Maybe if we just disassembly, we'll get a name. So there is interesting. This is actually interesting because I think it wasn't there when I tested. Wait a moment. Yeah, that's one of the problems trying to retrace your steps. So that at that time I didn't have the serial, and it might have something to do with the serial. So thanks God I didn't have the serial. Let's recompile. Compile and copy and restart this and debug. All right, so again, let's print out a vector table. Oh, yeah, as hexadecimal. And oh yeah, it still has like this entry here. Interesting. Okay, so yeah, anyway, when I tested it, there wasn't any interesting handler there. Let's check out the interrupt. Where is that interrupt? The list of interrupts. It's system description. I think here. It was like that list of table with all the interrupts. Moment. No, one before probably, yes. Yeah, so now it has a listener for IRQ0, but when I checked it, it didn't have a listener for this IRQ number 0. Not sure why. What is that? USB ISR, yeah, that's like for USB. So it didn't have this handler. Not sure why it has now. Maybe I was just lucky. I'm not sure what was different, but it didn't have. But it did have a listener for one of the other exceptions, which is I think this one, or yeah, I think that was this one. Let's see. Yeah, the SysTick. So SysTick is like one of the internal timers in ARM. It's built into the core. It's a part of the ARM core specification. It's not. You will find it in any ARM. I think. I'm not sure if it's optional or not. I think it's mandatory in Cortex M0. And you can see like, let's see. Oh, it's an optional timer. So you will find it in some of the Cortex M0 implementations. In this one, it's implemented. And you see this is like the ARM reference manual. It's not the RP2040. So it's like something that is part of ARM. And because I saw it had an handler for this SysTick, but it didn't have an handler for, I was lucky, and it didn't have an handler for those timer IRQs, I figured out that Delay probably uses this SysTick, and I should implement it. And I didn't really implement it because, you know, I just wanted it to work, and I also didn't want to take out all of the fun of implementing it from the live stream. So we are going to implement it today. But instead, I just wrote something that would just call this handler periodically, irrespective of like the settings and everything, just to test if it works. And let me spoil it a bit. It worked. So last week so this was like the last part that, the last piece of the puzzle that was needed for getting this blink to work. And with that, let me show you the very first version of this RP2040 code that we are writing for 15 weeks already, running inside Walkway. So there we go. This is like the Walkway Simulator, and you can see I added the graphics, and we have like an LED connected to GP1 and another one to GP5. And this is like, you have just seen this serial 1 trick, so it prints to the standard UART, and there we go. Let's hit play and see how it alternates between these LEDs. So yeah, so this is, you can already play it with it by in this URL, but I'm going to merge it tomorrow to just walkway.com, so it will be available as a part of the main site. To let the students of the course that we are starting tomorrow use it. So congratulations, we have a first working version that can be integrated into the simulator. And that was like 50 minutes of summary of about a day of work of fixing all those bugs and getting it to sort of work in the simulator. And this is far from being perfect. Like, we still haven't probably implemented GPIO. It's just output, and it's just one way of triggering GPIO output. If you remember, I think it was here. Yeah, like looking at these SAO writes. This is like a super, very basic working version, but it works. So I'm happy we have something to work with. And today after this very long introduction, let's get into work. So we did this. We got run Arduino core, not code, core. Yeah, we got it to work. We can remove it from the list. Now with timers, we are actually going to implement SysTick, and then we are going to implement GPIO. So to implement it, I mean properly, as much as we will be able to, and also implement GPIO input. And then there is one more instruction that I found we haven't implemented. Just running one of the tests, I noticed it printed these unimplemented instructions. You know, let's just start with it. To start with something real quick to just get us going. So ASRS, arithmetic right shift. We already got this instruction, but just not with 2 registers. So let's start with that. Then go with SysTick, GPIO, and I think at that point, simulator is ready for the course party popper. Yeah, so if we get here today, I'm super happy. If not, I will have to complete the missing pieces offline, at least the GPIO input, but I'm quite optimistic. And then for the next time, we'll talk about that at the end of the stream, but we have some surprise stuff that I didn't see coming before that we need to do before going to USB and PIO and MicroPython and CircuitPython and all of that fun. And we also have this tech debt. All right, let's get to work. ASRS, so RB2040 spec and RD2040 TS. So where that? So we already have ASRS just with immediate, and we are missing the register version. So as usual, let's start by writing the and thanks. Oh wow! Thanks for all the happy emojis in the chat. I really appreciate that. Yeah, let's implement the encoding. Oh no, I don't want the spec file here. I want the implementation ASRS register. And this one takes just 2 registers. We'll implement it in a moment. Let's just first add the test case. Should correctly encode, and that was the instruction. And do we have like the opcode for that? Did I? No, I didn't copy it when I copied this. Anyway, this is easy to fix because we can just compile this instruction. So let's, we have this blink. Let's just, add here ASM, ASRS, and then let's build it and see what comes at the other end of the pipe. So compile, error. Doesn't work. Instruction not supported in TAM16 mode. ASRS R3 R4. Okay, so let's just do it manually. Where was that? It was here. ASRS, and there is like. It shouldn't be too hard to just get this manually. Let's see. So ASRS, where are you? Test code. Oh, maybe ASRS. Oh, maybe we also need to repeat the second register twice. D and M, D and N should be the same. So let's try that, and if it doesn't work, then so maybe this is the instruction. No. ASRS. Oh, that's the syntax, I guess. Okay, it's not happy about it, so let's do it manually. I mean, that's just a waste of time trying to please the compiler here. Right, so this should actually be, so this one all those bits, and then we also want that was RM. We said we want it to be RDN RM. RDN and RM. So RDN should be the first operand, so that would be, and the RM should be the second operand, and the second operand is 4. So where are we? Yep. So yeah, so now we have to encode 4, so that's 1 0 0, and then the second one is 3, so that's 0 1 1, and that's, if I did this correctly, then this should be the opcode, the result, and if not, well, let's see. Anyway, then the encoder should do just the reverse of what we just did here. All right, 0B this, and then that's shifted by 6. And then we have RM, right? RM and 7, because that's 3 bits shifted by 3, and RDN and 7. RD, wait a second, RM, RDN, and RM. Oh, and we also need to change this to use this one. Why doesn't it work? ASRS reg, didn't it import it correctly? ASRS reg, yep. Okay, and this is not green, not fun. Oh, there is no 31, but it's probably, oh, yet. We wanted it to be R3 and R4. Okay, it's green, perfect. So we did it great. I mean, we did it good, it works. Now let's write the test case for the actual instruction. Now that we have the assembler, ASRS, and let's just copy this one, and R3 with R4. R3, R4, encode ASRS reg, and let's say that R3 is this. I think it's going to shift. Let's see what it does. It shifts Rn by, so it takes 8 bits from RM, then it shifts Rn by that amount, and then it updates all those flags. So Rn is this R3. So this is the value that is going to be shift, and this is shift right, and it's arithmetic shift, so it shifts in copies of the signed bit. Cool. So we are going to shift it by let's say, and let's have the I bit set to some, let's have some garbage here like FF50, but this is the actual shift amount because it's going to take just the low byte as we see here, like this as the shift amount. So after that, we expect R3 to equal, this should have been shifted by 7. So actually, it should probably be this, right? Let's double check this. So this shifted by 7 as unsigned to string 16. Yeah, cool. So this should be the result, and then that's negative, it's non-zero, and there is no carry because we didn't like throw out. Actually, let's add a carry. So now there should be a carry if there is a 8 here that we throw out when we shift those bits right. Cool, now let's try to implement this instruction. ASRS register. So encoding for ASRS, so this is the encoding for the instruction, and we are going to check whether we have yeah, whether we have this. I'm smiling because I'm reading the comments of the chat. All right, so there is like probably, yeah, we can copy paste the decoding from another instruction, and then rm and const, how did we call it there? Like the shift amount, shift n. Shift n is just registers at rm, and the input is actually rn, not confusing at all, rdn. Right, shifted by shift amount. Right, I guess. What is the thing about the 0? Oh, okay, we'll have a look in a moment. All right, so this is just taking the low byte, the shift amount from the RM registers, and then it shifts it, and then RDN gets the result. And finally, yeah, we have to calculate a carry. So we just do the shift by -1, and see if this bit is 1. And okay, this didn't quite work as we expected. Let's see, result to string 16. Yeah, I think it's okay. Let's make it signed so we can see. Okay. Huh? Well, where is that one? Where did that one come from? Oh, we shifted by 7. So, yeah. So, okay. Yeah, the test case was wrong. This bit, we shifted 7 bits. So if we wanted to get rid of this bit, we should have like have the 7th bit set, and we set the 8 bit. So we didn't get rid of it. Anyway, now the test case is correct. It passes. Cool. We have ASRS register. I hope the implementation is good. Like, it seems pretty good. Let's see. What does this do? If the shift amount is 0, it's probably doesn't. Oh, I forgot to see. Yeah. So here we have. So I'm worried about this condition that we have here, whether we should, why is the result 0 if IMM5 is 0? That's the thing I'm worried about, whether we should, I mean, I don't see any mention of it here, so it might be a part of this, and we may also need to implement it here. So let's see. Shift C, that's ASR shift with N and the RN. And Shift C, if it's ASR, it calls to ASRC, right? Ooh, but if amount equals 0, then nothing happens. That makes sense. So I think, yeah, so why did we have this? If maybe this is a bug, if the result equals 0, I mean, if the shift amount equals 0, then we return 0. That's strange. I think we don't have a test case for that. Interesting. That could be a bug in this implementation, like that's ASRS. I mean, it makes sense to me that if we shift by 0, then nothing happens. RD equals result. Yeah, this seems like a bug. Let's add it to our to-do list to check what happens when we have shift amount of 0. I mean, that one makes sense to me, because it just if there is if there is 0 shift, and I think we should do it as well here, like if we haven't shifted, then shift n minus 1 will be shift n will be -1, and I'm not sure how shifting by -1 works, so let's just make it shift by 31 to get just the highest bit set as. Actually, I think in this case, if the shift amount is 0, then the carry is not changed, right? That's what it's ASR. Yeah, that was ASRS, which calls shift C, and then shift C says, yeah, carry out equals carry in. So I think in this case, we just say that we only modify the carry if there was actually a shift. Okay, so yeah, now this makes more sense to me. This still doesn't make a lot of sense to me, so let's take a note to take a look at that, add it to the, it's not exactly tech debt, but what happens when we shift by 0. Anyway, I don't think this should be a common thing to shift something by 0. Maybe this is the implementation of move or something like that. No, there is like a different instruction for move, right? Yeah, there is a different. So shifting by 0 doesn't make a lot of sense to me for the most part. So we'll take a look at that in the future. For now, we'll just be happy with the new ASRS register that we got. Let's just take a look at the commit before we commit that. Okay, so we added this instruction here and the test case, and then we implemented ASRS register and probably found some bug when shifting by 0. It seems buggy. Maybe I should go back to the stream where we did that and see why I did that. That's another way to figure out if we... Oh, I didn't do that. Interesting. That was Brian who did that. So, Brian, if you are watching this stream, I would love to know how you came up with this logic, because I think it's not correct now when I review it, implementing this. It seems incorrect. So if you have any notes on why you did this, or you also think it should be changed and you are watching this, please let me know. All right, and the assembler, just adding this. Okay, let's implement it. Fit up it 2040 implement, or just ASRS register. Cool, one more instruction to go. I mean, a few more probably to go, one more done. All right, so we are done with that, and now the next thing on our list is to implement SysTick. And SysTick is actually quite simple. You know what, before that, I would love to get rid of some of this spam that we are getting here, all those undefined rights. So let's spend like 10 minutes just cleaning out the noise from the output. We don't need all of those rights. So I think last time, first of all, there is like all these rights here, and if I'm not mistaken, that's the USB. So for now, let's just make all the USB rights quiet until we get to the to actually implement the USB. So let's add another if here, else if that would be address USB control base address USB control base plus, where is the end of that? Yeah, I guess this ends here. So that would be the the range. Ignore these writes for now. Okay, and let's implement this USB, like the constant const USB control base equals this. All right, just reducing the noise that we get. Okay, so the next thing that appears, oh, we still get those. How comes? Right to undefined address. We just ignore them, I guess. Address. Oh, wait a second. That seems. Yeah, that seems in the range. So why is it like the same run, or are we looking at the previous run? Or, oh yeah, we are looking at the previous run. So yeah, we got rid of them, and now we have all of those. And last time I think we looked into those. That was this one, and we saw that we are actually generating those writes in the. They are part of the built-in registers for the ARM Cortex M0. We also have SysTick here, so and the interrupt controller that we implemented last time. So let's just implement those two registers, SHPRs 2 and 3, and the result value is just 0. So where are you, SHPR? That's the stuff for the let's store them. M0 plus built-in register. So there is like there was SHPR2 is 0 and SHPR3 is also 0, and at some point we probably need a better way to manage those. I mean, yeah, we probably need to find a better way to manage them, but for now let's just have them as constants here and add just a set of read hooks. It's actually a part of the NVAC, I think, those registers. So when we read from offset SHPR2, return SHPR2, and same for SHPR3. SHPR3. And then write hooks dot set, and then whenever we write to SHPR2, I think I just want to double check that no, that write has is getting the it's getting the address. I remembered we had a problem with that in the past, so let's just ignore this, the address, and save the value. So this is 3 and this is 2. Maybe just like that. Yeah, we can probably refactor, and we should probably refactor this to have something that just defines the registers instead of writing all this code. But for now, let's just make sure it works. Oh, we need to define those offsets, right? Need to find out why TypeScript is suddenly doesn't find the types for Node.js. I think we have those in yeah, we have those in the package.json. Maybe we need to npm install again. Anyway, so offset shpr. Oh, we already have those. Nice. We already added those offsets. Anyway, let's see if TypeScript restart TypeScript server is now happy about that annoying issue. And now let me just double check the code to see that I haven't done any stupid mistakes again. Okay, 2233 and value seems about fine. Anyway, now we should see a lot. Okay, that wasn't oh, it's already running, so it can't listen. Now we should see a lot of less like messages. It's still like there are still quite a few, but it's much better now. One other that we can quickly solve is like this MRS with unimplemented sysm value. So let's see what is, yeah, 3 is XPSR. So let's just implement. I think we already have a setter and getter for that from GDB. So that should be write spatial register, and this time, so this is 5, right? So let's add it here. This time I'm going to add the break first, so I won't forget it. I learned from past mistakes. So here we go, right? And let's also implement read XPSR, return this.xpsr. Cool. So one less annoying output message, I guess. All right. Cool. Yeah. So yeah, so we still have pretty long chatter here, but it's more tolerable than it used to be. And I guess we probably don't need those reset space. I think it just, if I remember well, this is just like doing, not sure. Where is that? Yeah, it's like a list of 2.10. What's 2.10? Yeah, probably that's just taking care of like chip reset and stuff, and we don't really need that, I guess, in the simulator right now. Just resetting some peripherals or something like that. So we'll probably soon remove those messages as well. And SPEDs and IO are going to be handled by the GPIO. So yeah, we still got some work to eliminate all of those. But for now, let's just commit what we have so far. Fit RP2040, reduce console log chatter, implement sysm. What's sysm? Oh. MSR MRS with XPSR sysm3, so this one, and then we also implement how did we call those two register? SHPR. That's the priorities for the I think we did it 2 streams ago, those registers. Oh, now I also know why we have those variables, because we already use them. We read from them, but we haven't implemented like the storage for them. So like getting priorities for the SVC that we implemented, I think 2 weeks ago or last week, not sure. Yeah, I think it was last week. Anyway, we implemented that, and stop writing or don't report errors writing to the USB controller. Cool. So some less output to confuse us. Okay, so now let me take a sip of water and let's do the SysTick. SysTick. There we go. So fortunately, the SysTick, I think, yeah, we have the registers somewhere. SysTick. Yeah, it only has 4 registers, which is nice. There is like control and status register, reload, current value, and calibration value. And this one has like a few bits, and this one is read only, and it's okay. Returns this one if this timer counted to 0 since the last time it was read. Clears on red application or debugger. SysTick log source, external reference log, processor clock. Tick int enables SysTick. So this is probably enabling the interrupt, and this is enabling the counter. And then RVR specifies the value to load into SysTick current value when the counter reaches 0. So it counts down, and then at some point it probably reaches 0, and then it's reloaded with that value. And this is like the counter, the value of the counter. And then we have this calibration, which those are it's read only, and it returns the optional reload value to be used for 10 microseconds. Timing, subject. Okay, so this is a value, if I understand correctly, that we can put in this register, in this reload value here, so that SysTick happens every 10 microseconds. So how many clock cycles are there in 10 microseconds? And let's see if there is any more interesting information about how this works. What are all those? ICSR, okay, interrupt control. Yeah. Isn't there like any information about, like, is it using the system clock or, oh, wait a second. SysTick extend both 24 additional configurable priority SysTick. 1 microsecond pulse as the clock enable. So it probably ticks every 1 microsecond. It counts the number of microseconds, if I understand correctly. Let's start with just, adding those register values into our code. Again, it's like in the same PPB base, under the same PPB base region. So CSR equals, let's keep them consistent with the others. So there is CSR, which is SysTick control and status register. Let's add that as a comment. And then there is the next one is RVR, which is SysTick reload value register, and the value of it is 14 at the end. And we have CVR, which is current value register, and they are great at coming up with very confusing similar names. RVR, CVR. Anyways, let me stop complaining and start writing some code instead. And finally, a name that is a bit different from the others. Calib is at 1C, right after this one. And this is SysTick calibration value register. So, yeah, let's start with implementing this register because it's read-only. So I guess what we can do, we can just connect to the actual Pi 0 and just print the value of this register. Ooh. Oh yeah, I remember I had some issues with my network, so I disconnected and I'm now running on my broadband connection. So let me try to reconnect to the LAN, and let's hope that won't interfere with the stream too much. Yeah, you can see I got disconnected from the Raspberry Pi. Let's see if it works now, maybe. Yeah, okay, fingers crossed that this is not no internet. Doesn't sound very good. Okay, I will try that again. Okay, so So yeah, the good news, I managed to connect to the Pi now when I switched networks. The bad news, or I don't know, are we still on? Let me know in the chat if you can now see me again after I switched connections. Meanwhile, let's restart GDB. Now it should connect to the Pi Pico without a problem. So I'm looking at the chat. Let me know if I'm back. Okay, and now we're going to print the value of this register. Okay, thanks for the feedback from the chat. I see that everything is fine. So I'm printing the value of this system calibration register. No, I just want single. And this is the value of this calibration register. So it's read only, and this is the value we read from the actual Pi. So let's edit. So this is SysTick, and yeah, we should obviously read hooks. We should obviously refactor this at some point to smaller files, and I think we'll do it next session. I will tell you why in a moment. Anyway, SysTick, that was offset, SysTick calibration, and let's just return this magic value that we just read from the Raspberry Pi. And if we look at this value, that should be the number of ticks to get for 10 milliseconds. So if we know the tick happens every microsecond, oh, where did it go away? Yeah, here. Okay, if we know that this SysTick clock happens every microseconds on the Pi Pico, we know that for 10 microseconds we need 10,000 of those, so we expect this value to be around 10,000. Let's print this as unsigned int. That didn't quite work. Oh, unsigned int pointer, no. Yep, now the value of it. No, yeah, okay, printing it as decimal finally. So yeah, so that's around 10,000. I guess the reason for that is that it counts to 0 and then it goes back to this value, so it's actually counting 10,000 times before it fires the interrupt. So yeah, so that's like a constant value that we give the code. If you want to get SysTick every 10 milliseconds, then just use this value. And now let's see, we have this SysTick reload value. So let's have a variable for this as well. SysTick reload equals 0, and then we can read and write from this register to control it. So SysTick this.readhooks.set ppb base plus offset SysTick reload value returns just this SysTick reload, and then same with the write hooks of SysTick cover. This does SysTick reload equals value. Okay, and now the interesting part, which is reading and writing from the actual SysTick counter, and then also raising the exception. So first of all, we have the SysTick control, which has those tick int and enable and clock source that we probably want to keep track of. So let's create something to hold that. SysTick control, and yeah, the reset value is 0, and also RVR. Oh, it's actually unknown. So 0 is definitely unknown. Okay. All right, so yeah, and this, okay. So let's implement reading SysTick control. RVR and CSR, just return. Okay, and now we also need to do count. So we only need to return the low 3 bits from this SysTick control. Set if yeah, let's have a value for that. So let's have SysTick count flag. So SysTick count flag will be set to true only if the timer, whenever the timer counts to 0, and whenever we read from this CSR register, we just clear the count flag. So yeah, where was that? CSR, yeah. So const count flag value is this dot count flag. Then we set bit number 16, otherwise it's 0, and then we always clear this flag whenever we read, and we have that logic implemented as well. So this one as well. And finally, so we have this, and we need to be able to return oh yeah, we need to implement write to SysTick. Set ppb base plus offset, that was SysTick CSR. So this dot SysTick, these are the only things that are read write. So SysTick control equals, and we have here address and value, that value, and we take only the lowest bits of the values of the value, like those 3 bits. Okay, and now we are only missing one register and also the logic to update SysTick and to fire to raise an exception whenever it goes to 0. So yeah, so first of all, we can like do it sort of naively by yeah, we can do it sort of naively by, you know, just incrementing it every microseconds, but that would probably, I mean, JavaScript doesn't really have a timer that fires every microsecond. The resolution that you get from timers is millisecond resolution, not microsecond. So we could either implement that as sort of like busy waiting, checking after every instruction, and that would probably slow down the simulation, really slow it down. Or we could just, you know, sort of fake the counter value. So keep track of the last time, the last time it was reset, and then calculate the delta, the time until it needs to be reset again, and then just, you know, fire the interrupt at that time, sort of create a timer that would do that. And for that, I would actually, yeah, I think the best way to do that is to actually create some utility class that would help us to manage the clock. So let's call it clock.ts, and then we have export class clock. And one of the things we want to do in this clock is to make sure that this clock sort of stops ticking when we stop executing the code. For instance, when we hit a breakpoint. Otherwise, debugging will really interfere with this virtual clock. I mean, even if in the actual microcontroller, I can show you that. I guess that if we read this counter, let's read it for a moment. The current value, where is that? This is the CVR at 18. So if we read it, you can see like it doesn't change. And then if I go one instruction, then it will probably go, oh, it didn't even go down. Yeah, it's probably stopped, I guess. Let's start a simulation for a moment. I mean, this is not the simulation, the actual Pi. And let's print the value. Yeah, and now if I go one instruction, yeah, you can see like now it's in this idle loop, and it slowly decrements on every instruction. Like that's the number of microseconds it takes the microcontroller to execute that instruction in debug mode. Pretty long time, I would say. Like 8 microseconds for that, for a single, or yeah, 8 microseconds for a single instruction. It seems pretty consistent. But yeah, you can see like it's stopped unless I execute an instruction, and then only then it advances. So we want to stop the clock while we are not running instructions. So let's have like base time is a number, and we have a start method, and or maybe reset method that resets the clock, and then this dot base time, let's say it's 0 equals, we have this, I think, yeah, get current microseconds. That sounds about right. Where did we use that though? Why doesn't it import it? Imported from utils time. All right, import this. All right, and then yeah, so we can get micros that will just return get current time minus this space time. So basically, whenever we want to get a current time, we just subtract the time, the number of microseconds that passed since reset. And why doesn't it? Oh, it's in the current directory, I guess. Yep. And let's add this clock to our RP2040. Yeah, it could be here. Read-only clock is new clock. All right, we have this clock, and then we can do inside the constructor, just, you know, or maybe inside execute. That would be a better place to yeah, this dot reset, or I think we are calling execute from GDB when we resume, right? So actually we want to resume the clock when we are, so let's start a clock paused, and then we can probably resume it. So yeah, let's make the clock so it has pause and resume, and then we can whenever we pause, we just note the base time where we, or the, yeah, the time we paused it. So that would be how much time. So yeah. And when we resume, we can say this dot base time equals this dot pause time minus, no, this dot So sort of tell it to set a time to the base time to the current time minus the time that it's passed since until we post. So when we pause, we just this.getMicros actually. It does the same thing. Actually, we can turn it into a proper getter, so we don't have to type get every time. All right, so yeah, so now we can say in the constructor this.post time, or maybe we can say it's posed. So we can just say posed equal true, and then resetting it. We don't actually need to reset it at the moment. We don't need to implement that. So if this.posed, or if not, this.posed equals true, and then resume if this.posed, then this.posed equal false. Okay, so this is sort of a poseable timer that we should be able to easily pose whenever we want, and just take note of the current time. And now inside the execute, I think we already sort of resumed it, and whenever we stop executing, we can just this.clock.pause. So whenever we GDB stops running, we should just, you know, pause the timer. Yep. Yeah, this should probably work. All right. Cool. And now for the SysTick. So whenever we want to get the current value of SysTick control, SysTick last reset is 0. That was the last clock when we reset SysTick. Yeah. So initially, let's say or maybe SysTick last 0. All right, and now when we read from the SysTick value, so that would be reading from CVR current value register. Thanks, I gathered the comment, so we know this. So this.clock.millis. So let's see. Const delta is this dot. Why doesn't it? Oh, that was micros. Minus this dot SysTick last 0. So if there was if there wasn't any delta, so it's still 0. Otherwise, return this dot SysTick reload. So this is like the value that SysTick was immediately initialized to after it was zeroed out, minus this dot SysTick minus delta. So if there was, minus delta plus 1. So if there was if 1 microsecond passed since SysTick was last zeroed, we would get the SysTick reload value, because then delta would equal to, actually minus 1. Delta would equal to 1, and then we would get just the SysTick reload, and if more 10 microseconds have passed, then we would get SysTick reload minus 10. And that would, of course, work only if we always update SysTick last 0, or we can just, delta this dot SysTick reload +1. So basically make sure this value is always in this range, and then the result will always be correct even if we haven't updated SysTick class 0 for a long time. So it seems to be good. And then next thing to do would be to create the right hook for this. So right hook, and then address value, and then we just need to sort of work back. Yeah, we should also do, I guess. Yeah, I guess we should also do this when we do this SysTick reload. But you know what? Let's not worry about it for now. Console.log SysTick CVR not implemented yet. I guess that in most cases, let's also print the value. In most cases, people won't set the value of SysTick, or let's actually see if anyone uses it. Otherwise, like we need to implement it, but I think all that math will take a long time to implement, and I don't want to do it now. We still have a lot of other stuff to do. Oh, we have an unimplement instruction. What's that? Not again. Let's see what's there. So target remote. Oh, we don't want this. Did it even compile? Anyway, disassemble. What's here? That was at 6A. Where is 6A? 6A, DSB, ISB. Yeah, probably this DSB. I don't think we implemented DSB and ISB, right? So yeah, let's /R to get this. Okay, so we also need like to ignore those instructions so they won't interfere with the code. So let's add it to the to-do list. These are just like I think we also already implemented MSB, so I'll do it for the next time. Implement or skip. This is like data synchronization barrier and instruction synchronization barrier. We don't really need this in but decode them in the simulation. So again, if you feel like, just send a pull request and I would happily accept that. Right, anyway, let's get this SysTick to work. So yeah, you can see there is like no, I don't see. Yeah, there is like one write. Interesting value. Is that like this the hexa? Maybe I'm mixing up the value and the address. Yeah, I am mixing up the value and the address. Why do they do it? I think, did we mix them up here maybe? Right hooks. Yeah, I think we did. I think we had a bug and we fixed it. And now we still haven't fixed that, like function signature, right, uint32, and then if we don't find them, yeah, value and address, even though hook, like, is defined. Yeah. So good that I caught that in time. And now, yeah, it makes much more sense this way, because most of the time we are not really interested in the address. So let's go back to the instructions, things we implemented today, and fix that. So yeah, So one bug removed here, and all of those fixed as well. Okay, and now it will probably make the value they write here will probably make more sense, the current value. And since there is, for now, there is like only one right there, I think, yeah, we are just writing 0. I think it doesn't matter if we don't implement it right now. Anyway, the next thing we need to do is whenever we enable this timer, so let's print SysTick value.string 16. So whenever we enable that timer, we should actually start like firing those interrupts. Where are you? SysTick. Yeah, you can see we are writing 6 and then 7. So 6 is SysTick control. 6 means we are enabling the interrupt and setting up the clock source, but then we enable it. So in this case, I want to do this. If this.SysTick or if value, let's see, const priv enabled is if this.SysTick control, or yeah, it would. So I'm checking if it was previously enabled, and that's SysTick control. And now I'm checking if it's enabled now. And then if this.priv enabled, yeah, yeah, it's actually checking if the it's enabled, and maybe we'll call it priv interrupt and interrupt. If it's enabled, then it should fire the interrupt, which is just it's still not covering all the use cases, just this use case we have here in link. So if interrupt, then okay, if interrupt, and then we should fire a timer that will you know, just so let's implement this. Yeah, we can probably add this to the clock. So this.SysTick timer is this.clock.create timer that will run every, so we need to this.SysTick reload value, so every this number of microseconds plus 1. We are going to basically this exception entry. That's how we trigger an exception. And exe SysTick. Yep. So we are going to so this is whenever the SysTick resets, and again we should probably adjust it based on the current SysTick value, but I think for this, in this case, maybe to do adjust the timer based on the current SysTick value, at least like for the first time. Else is.clock.delete timer and SysTick timer. Okay, so otherwise we want to just, you know, remove this timer, this.SysTick timer, and we need to implement this timer mechanism now. All right, so let's add this timer mechanism to the clock, and yeah, so create timer, and create timer basically get delta how many millis, until this timer fires, and callback. And then let's have class clock timer, and it has a constructor with millis and a callback. That is a callback. And the reason I'm I'm going to create like a list of all the timers. So in case we are pausing, we are going to disable them and then re-enable them again. So or maybe, yeah. So whenever we have a new timer, we just return this timer, this dot return new timer. New clock timer. That will fire delta micros actually after this at this time, and the callback will just remove this dot timers. Let's have a list of all the timers. And then this dot timers dot remove, or it can be a set to make it set of clock timer. Cool. This dot timers dot remove. Yeah, we are going to remove the timer, so we keep track of it, and then call the callback the user provided. Delete. And let's add it to our timers list, add timer, and return it to the user. And then whenever we want to cancel it, delete timer, delta micros. Oh, no, we just want the timer, clock timer, this dot timers dot delete timer. Now, the last thing we want to do, we want the timers to actually fire. So let's create a schedule method, and this dot JS timer. Not just JS timer. This will be private JS timer. Is basically we are going to schedule it as soon as we create it, so we can initialize it to 0, and then JS timer is this dot, and that's micros not millis. Set timeout, and then this dot micros we need to multiply it because set timeout works with millis, and then just call this dot callback. If this dot JS timer, then we also this dot so this dot JS timer, set timeout, calling the callback after private, and I will make this private as well. All right, so yeah, again the same thing with Node.js timeout. How did we had this problem? Yeah, here, Node.js.timeout, that's the type. Cool. All right, and then unschedule, we'll just this dot clear timeout, this timer. So this will allow us to pause and reschedule the timer. So let's start with null. Cool. And then if this .js timer, then just cool. And now whenever we are pausing, we are going to update all the timers. So for const timer of these timers, we need to unschedule them, and we also need to update like the amount of time left. So basically yeah, we can probably So when we resume, first of all, we for const timer of timers timer.schedule. And then when we delete a timer, we also want to timer.unschedule, so it doesn't fire. And when we add a timer, we want to schedule it, timer.schedule. Cool. And then finally, when we pause, we want to take note of the time left. So let's have another like public time left, or yeah, we can call it time left. So whenever we or maybe we can just, you know, add pause and resume methods to the timer, and it will take care of this logic. So private time left, so pause and current micros. This dot time left is just like the micros minus current micros, so basically just and then when we resume current micros, we can just this dot micros equals just do the opposite, current micros plus this dot time left. But obviously current micros will change by the time between when we pause and resume, and we pause, we unschedule it, and we resume, we schedule it again. All right, and then we can call it just here, pause with this dot micros. Jim is asking in the chat if the project is in React.js. So the RP2040 is just pure JavaScript. It runs in Node. It runs in the browser, and the Walkway Simulator itself is written in React.js. And if we didn't have the course tomorrow, I would probably wait with this integration and would probably do it in like 5 weeks or something like that. And before that, I would just create a smaller demo app in the browser that would use the simulator. And we'll do this, but first I just want to make sure we have everything ready for the course. So is there a problem with the stream? Somebody is saying there is an issue here. Okay, so yeah, it's not something for everyone. Anyway, so I hope that like by the end of the month we'll also have a smaller demo project on StackBlitz or something like that that shows how to use the simulator on the web and connect it to LEDs like we are doing here. Just because of the course, some of the priorities have changed. Anyways, so I think we have like more or less this implementation of timers here. So yeah. All right, so now we can go back to this SysTick and just now we have those timers, so we can just add this SysTick timer member. So if interrupt and not prev interrupt, so if this has changed, then we need to enable timer, and if prev interrupt and not interrupt. So if it was disabled, we'll need to disable this timer, and let's just create this. Yeah, let's export this class clock timer or null equals null. Cool. I think we probably have a lot of bugs because, you know, I wrote this code real quick and I'm a bit tired already. But you know what? Let's run it and see. Why isn't it happy? Oh, yeah, probably we can do it if it should always be true, but better than be safe than sorry. All right, so let's just run it and see if it magically works, and we get an error, of course. Yep, what happens? Time left, there's no initializer. All right, so we can say it's initially it's just those micros. I mean, it doesn't really matter unless the timer has been paused. All right, let's see what happens. GPIO set to high and nothing. All right, let's see if we are so Jim is asking about the course, so I think we have it open here. It's this one, yeah, Raspberry Pi Pico and the RP2040, the deep dive. So I will also post the chat on the link if you want to check it out. It's similar to the AVR course that I did a few months ago, but for the RP2040, and it's basically based on all the insights that I gathered in these streams, but it's not focused on creating the emulator, rather on understanding the architecture of the chip. So a different point of view. All right, let's see. Let's console log here and see if we console.log enable SysTick. Let's also console log write Sysd CSR value, just to see that this, I didn't want to exit. NBM start. Okay, I think I saw something. Yeah, enable SysTick. So this gets here, so we know it gets here. Let's say, let's see if there is any SysTick exception. And let's also print the value the value of the reload, like how many milliseconds until the timer fires. And thanks for following, Jim. Thanks for following the course. So yeah, that's 120 microseconds, so 120,000 microseconds, so 120 milliseconds. So yeah, so it should have set up the timer. Let's see if there is, like, normally if I had a time, and I might be sorry for doing this, but if I had a time I would probably write test for this, but yeah. Schedule the timer, and then yeah, let's also print console log timer callback. Oh, I think I know what the problem is. I think we are probably firing this timer, scheduling it, and it probably fires at some point, or it doesn't. It doesn't seem to fire. Oh, wait a second. We need to divide it by 1000, not multiply it to convert it to microseconds. Right, so now it should probably fire. Yeah, we can see there is a callback, but it's only called once. And the reason for that is that, whenever there is the callback, then the timer is deleted and goodbye. So let's remove all the console logs from here and keep them concentrated here. And so whenever we let's call it const SysTick callback equals this, and then whenever this happens, we just reschedule the we just reschedule the timer with SysTick callback. All right, so there is this to do, but let's see if everything works well. We'll get a bunch of those callbacks. Okay, it didn't work well. Oh wait, we may get them, but we removed console.log SysTick callback. Okay, we should get a bunch of those callbacks, and then it should like exit delay. well, one, yeah, they are happening, but it seems like they take a lot more than 120 milliseconds to tick to happen. So that's interesting. I mean, let's just, you know, const log the value we pass to a set timeout. Oh, wait a second. Yeah, I see the problem here. Yeah, this is like micros is like, yeah, it's like this is relative time to the current time. In micros is absolute time in terms of this timer. So whenever we call schedule, which I think is here and also in pause, we should also pass the current micros. Yep. So let's current micros number, and then we can just use this relative number, current micros, and here when we call schedule again, we need to pass this micros. When we actually, we can just call timer, we should just call timer.resume this.micros, and when we schedule this.micros. Okay, and Jim is asking if I'm teaching in some institute. Not currently. I used to teach in the Technion, which is one of the Israeli universities. Oh, well, wait a second, what's happening here? Whew. So I taught their web development course some time ago. So it seems like the timers are working, but maybe they are working too good because we are getting some kind of exception. And my guess is that we are probably firing a SysTick callback at the wrong time while an interrupt is executing or something like that. So, you know, exception entry just checks if takes the exception. So instead of that, we should probably do something like we do with the interrupts, like we do with SV call. So we probably also need to do this with SysTick. So instead of like saying that, hey, execute that interrupt now, no matter what, we should just have a pending SysTick. So SysTick, maybe we'll do it here with the rest of the interrupts. Pending SysTick boolean is false, and then instead of like SysTick, instead of like firing the exceptions right away, we can do this dot pending SysTick equals true, and then this dot check for interrupts. And inside check for interrupts, or no, we have like I think this dot interrupts updated true. So this will make sure we call check for interrupts in the future, and then yep, and then we have like inside check for interrupts, we can add a similar test. We can add SysTick priority, which we'll implement in a moment, and then do the same with SysTick. So if it's pending SysTick and the priority is SysTick priority, then just call x SysTick. And SysTick priority, what are you SysTick priority? So as we call priority, and then let's see where it reads the SysTick priority from. So probably from SHPR2 or 3. Let's check out the datasheet. SHPR2 is as we call, and this is SysTick, so SHPR3. Same location, different register. So SysTick is at SHPR3. All right, so with that, we may fix the bug that we just introduced by, randomly calling SysTick or always calling SysTick no matter what the current the processor is currently executing. So now we take care of running it through the standard interrupt priority system. And all right, it doesn't crash, but it's still stuck inside delay. So GPIO pins 1 set to high. And I think that was more than enough to... So let's go into the debugger and see if this exception vector is actually getting invoked. So yep, target. Why isn't this stopped? Interesting. It seems like something is strange here. It seems like the callbacks stop when we run the code. It seems like we are having some problem with resume and pause. But resume somehow, right? Resume clock. Pause clock, and that's also SysTick. All right, let's console log that here and SysTick. Yeah. SysTick exec, just to make sure, like we hit a callback, but let's make sure it's actually executed. Ooh, a lot of resume calls. But yeah, I guess this is caused because execute is just, you know, calling clock.resume every time. So let's remove this debug print, or maybe let's just print it if we are already paused. And let's npm start again. Okay, it seems like it doesn't execute very often. Like there are a lot of callbacks that doesn't get executed. Interesting. Why is that? So let's see, we set this pending SysTick to true, and then interrupts updated. And I think setting interrupts updated to true should make it check for interrupts on every before every instruction. So as soon as it's ready to execute, it should execute it, and it's the only place where it's set to false is like inside check for interrupts, and it won't be set to false. Wait a second. Yeah, I think we should only set it to false if we are at the lowest priority level, because, or when we change priority level, we should probably set it to true, do we? Setting ISCR, we check when we exit. This is like exception return, and I think after exception return we updated ISPR. So we should also set interrupts updated to true, just to make sure. All right, just to make sure that now that we returned from an interrupt, we'll in the next instruction we'll check if there is any other pending interrupt. That makes more sense. Okay, so it still haven't fixed the bug though. Like it's executed only once in a while. Let's console log the entry and return. Right, this exception number. Well, it could be that the callback, let's see where the exception number 15 that is taken every time we exec is the SysTick exception. So whenever we return, let's also print that we return from an exception. Right, return from exception. So we'll have some understanding of how long it took this exception to execute. Maybe it's just taking, yeah, interesting. Exception taken, that's 11 is not SysTick. What is 11? Maybe Svc call. Anyway, this is interesting. It returns immediately, but then on the next callback, it doesn't. On the next time SysTick is called, something strange happens. It's no longer inside an exception. So I wonder why it doesn't. Okay, I have another idea here. So yeah, exception check for, let's just do this. If this dot pending as SysTick, let's print checking for SysTick. And then we can also print current priority. All right. Yeah, we can see it's checking for SysTick and the priority is 0, which means it's, but where is the cases where, yeah, for some reason the priority is 0, even though, and I guess that's, even though it's not really running anything, maybe it's though, let's check the value of this.pm, which should disable interrupts because it sets the priority to 0. Yes, for some reason PM is true, so that's why we are not getting the SysTicks. And I guess we can try just to know to print the SysTick priority as well, but I guess that SysTick priority isn't going to be less than 0 because it can, yeah, it's 3. Interesting. So the problem is that this.pm is set, and why is that? And maybe, just maybe, yeah. All right, a second, yeah. So obviously, after changing the priority, the value of this.pm, we should also check for interrupts. This.check for interrupts, because it may have changed, or no, this.interrupts updated equals true, because this value also affects let's go back here. Yeah, because this value, this PM value also affects the interrupt. So let's try that again and see if we get any better result. Yeah, it seems better. It seems like now we have an execution after every SysTick callback, so we can probably we solved another annoying bug where exceptions were sometimes delayed for some distant time in the future if they fired when PM was true, and then the code set PM to false. Console log, don't need that anymore. And We probably don't need that as well, because now we see it's, or maybe we don't need a callback. Okay, so now we can see that SysTick is actually running more or less as it should, like every 120 milliseconds. But for some reason, it still doesn't make delay happy. And I'm not sure why. That's interesting. All right, let's remove those const log. And yeah, right. Do we have any const logs in the clock? Yeah, we have this. Pause. All right, so I wonder, yeah, we still don't get past that delay. I wonder if it's due to the fact, let's try to, speed up SysTick by a factor of 10 just to see if this, or even 100, just to see if this fixes the issue. So no, it doesn't seem to help us to blink. So I guess, yeah, I can't really tell what is the problem right now, if this is related to the fact that we saw, oh, it works, it's just really slow. You see, now delay passed, and for some reason it works, but it's super slow. I mean, now when we divided it by 10, it eventually decided to switch from low to high, but so either we have some problem with the math, even though it seems like we can exec, where is this SysTick pending? I mean, we know the value of clock dot can print the current microseconds, and we expect it to fire this dot fires every this dot SysTick reload micros. We expect it to fire every SysTick reload plus 1 micros. So now we can see if the math is right or if we have something else. Yeah, the sequence of numbers looks correct. Like, it seems like let's just quickly calculate the delta between two numbers. It seems like it does fire roughly every 120 micros. So I'm not sure what the problem is. Yeah. Anyways, I think it's time to wrap up. So we have working SysTick implementation, but for some reason it's super slow. And I guess there is like, ooh, what is that? But I mean, it worked a second ago before I removed this debug print. Okay, it works again. Strange. Maybe some strange timing issue. I don't know. Anyway, we have a sort of working SysTick implementation. I will, just like last week, I will take it offline and try to figure out why it's running so slow. But at least if we speed it up by 10, we can see that it actually goes from high to low and low to high. So Blink is working very slowly, but it is. And let's commit our work today. Yeah, we implemented, I guess, some of SysTick. There are like a few to-dos here, but for the most part, the basic logic, let's just remove this console log here. The basic logic is there. And there is probably some bug with the GDB debugging, because we saw that the clock is running while GDB should be stopped. So I will probably have to look into that as well. Do we have any console logs here? No, great. Feed SysTick, work in progress, SysTick timer. So not totally working, but I mean, it's working, but it works, but for some reason it's super slow. Cool. And yeah, you can commit. And let's just, release this new version and update our sort of improvised to-do list. Let's, for a moment, remove all those files so we can release the new version, npx np, and let's see. So this is, I will add a check mark, even though I still have to go offline and figure out the thing with the speed, but and we still got a few to-dos here, but it's usable. Unfortunately, we didn't get to GPIO this time, so I will probably do some kind of implementation offline as well, and then next time we'll just review it, just like we did with the bugs this time. Sorry about it, but we have a course tomorrow, so as I said, we have to shift priorities. But for next time, we're going to have something really interesting. So other than like these instructions that we need to decode, unless one of you wants to come up with a pull request, which will be really nice. The surprise tab is actually, I want to try to implement multi-core support. So, support core 0 and core 1 running in parallel, and that's because next week I'm going to talk about that in the course, so it will be cool if we have that in the implementation, and that would probably be a stretch to get it done next week, but we'll try. Yeah, so what happens? Yeah, we want to continue, and let's do it a patch version. We didn't really finish shipping the new feature. So that's the plan for next week, those, and going over whatever I fix in SysTick and some dummy GPIO, like some basic GPIO implementation. If you want, you can spend a week checking out the datasheet. There is like 2 sections that are related to the GPIO. First of all, it's the SAO. It got a bunch of registers that control the GPIO. Where is that? It's probably in the list of registers. Well, let's just finish the release. Cool. Publish. New release, congratulations. All right, so where were we? That was inside the SAO. Yeah, there was a list of registers. Yeah, so there is like a bunch of registers. You can see them here that like let you set the output value, clear bits, set bits, XOR them, then same for the output enable. And then there are like also here there is a whole section about how the GPIO works, and there are like 2 peripherals which I think we already have placeholders for. So there is like pads and IO, and you can see in the output the code is interacting with them to set like pull-up registers and stuff like that. So yeah, that's the plan for next week, and for me for this week. So I will see you again next Tuesday, or if any of you are taking the course, I will see you tomorrow. And if you check out walkway.com, probably at some point tomorrow we'll have this merged into the main version. I have a really intense day tomorrow to get this done, so we'll probably have this merged into the main site, and you will be able to start playing around with this. So I hope you had a good time and learned something new today. And see you next week. And until then, have a great rest of the week. Bye bye.